Swayam Prabha. Digital India. Educated India.
Welcome to the next session on the Organic Chemistry 2 paper. So in the third module, we are studying about how to solve problems related to alkyl halides reactivity. So the problem solving approach we are currently doing. In the lecture 2, we will be taking some specific reactions and try to work out how to solve or how to identify what is a product, or if a product is formed, how the product could be formed based on which mechanism. So all those things we will be studying. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayam Prabha, MHRD, New Delhi. So the topic that what we'll be covering is worked out examples of SN1 and SN2 mechanisms, and some tips on how to look for clues to solve these particular problems. Let us now look at a few worked out examples. We have studied so far about both substitution, nucleophilic, unimolecular and bimolecular reactions. Now we will be applying some of these reaction mechanisms to the reactions. Let us look at this particular example. In this example, we have a azide group reacts with a furfuryl bromide, and we need to find out what is going to be the product. So in this particular case, we are going to find it out what is the product when the azide anion attacks the primary bromide. So in this reaction, the obtained product is a azide, and the reaction proceeds through SN2 mechanism. So the nucleophile azide anion attacks the bromide with concomitant removal of the bromide anion. So this is how the reaction proceeds, and this is by the SN2 mechanism. So let us look at the next reaction. Here the phenoxide ion reacts with the alkyl halide. So the phenoxide anion is the nucleophile and we have a alkyl halide. The reaction is the same SN2 mechanism. So in this particular case, the anion attacks this carbon so that the chloride leaves and we end up with this ether. So this is the reaction mechanism is SN2 type mechanism. So that is the rear side attack of this particular both the substrates. Here the bromide is replaced, here the halide chloride is replaced by the nucleophiles. So this is an example for SN2 mechanism. Like this we can actually find out how the products are being formed. Now let us look at another example. In this particular case, we have a alcohol which is stereogenic center is present in this particular alcohol. This reacts with HCl and water. Let us see what is the product that will be formed in this particular reaction. So this reaction proceeds via SN1 mechanism. So as we had seen, this carbon is basically a tertiary carbon. So this carbon is a tertiary carbon. So the tertiary carbon generally undergoes reaction by SN1 mechanism, and we have a intermediate that is a planar intermediate. A planar carbocation is formed in this particular reaction. The planar carbocation can be attacked from either the top or from the bottom side. So this leads to racemization. So the carbocation can be attacked either from the top or from the bottom. So we end up with the product where the racemization actually takes place. Now you will be wondering, what is the leaving group and what is the nucleophile? In this particular case, the nucleophile and the leaving group are one and the same. So that means then how do we know the reaction actually proceeds through racemization? So if we take the optical activity of this starting material before the reaction and let us run the reaction for some time and then observe the optical activity of this final product that is obtained. So by this way we can actually figure it out. In this particular case, racemization does occur, and that is due to the SN1 mechanism. So you don't have to worry about what is the starting material or what is the product. The main thing what you have to remember always is what is the leaving group, on which carbon the leaving group is present, what is the nucleophile. So these are all some of the hints which will help you understand what type of a mechanism. In this session, we will also be looking at how we can actually figure it out, what type of different mechanisms are possible, and how do we figure it out what exact mechanism is applicable for what particular substrate. So if we take another substrate, here also we have a quaternary carbon. Okay, so this also undergoes acetylation. In this particular case, the carboxylate anion is the one which is the nucleophile in this particular case. So this carboxylate anion removes the chloride. So that means the substitution happens, chloride is lost, chloride goes out like this, and this basically here is a negative charge. So this negative charge comes and attacks this carbon. So we end up with a acetyl, in this case propanoyl derivative of this compound is formed here. Okay, so this is the propanoic acid. So the propanoyl derivative of this compound is formed here. So this is how in the SN1 mechanism we can very well say that is a planar mechanism, and how the groups are replaced we can actually see. So the first is basically the removal of the chloride that produces the carbocation here. So the carbocation is being attacked by this carboxylate anion to get the final product. So we will now look at a comparative study. So that means in this particular case, which substrate reacts faster for an SN2 reaction, and we need to find out why one of the substrates reacts faster than the other one. We have a primary bromide here. We have a primary bromide here and we have a secondary bromide here. So which one will react fast? Quickly you will think that primary bromide will not react faster, or maybe secondary bromide will not react faster. So we cannot easily say just by looking at whether it is a primary bromide or secondary bromide. We have some additional things also we need to look at, that is the steric nature of the reacting center is very essential. So what is required? The steric nature of the reacting center is the one which actually decides which one will undergo reaction faster. So as I mentioned, we have to look at this one undergoes, this substrate undergoes reaction faster compared to this one. That means the secondary bromide reacts faster than the primary bromide. But you already know in the case of SN2 mechanism, basically the methyl group reacts faster, followed by primary, followed by secondary, then tertiary does not undergo reaction by SN2 mechanism. But in this particular case, we have a different observation, because we cannot always consider that primary is the one which always reacts faster. So here the steric nature of the substrate also plays a role, very important role in deciding which one will react faster. Now one thing you have to remember, what it is, both the substrates undergo the reaction. It is not that one only undergoes reaction, other one does not undergo the reaction, is not the case. Both undergoes the reaction, but at what rate? Which one reacts faster and which one reacts slower? This is the one we are actually looking at in this particular case. So don't get confused by whether this will undergo reaction by one mechanism or not. We are not looking into that aspect. We are only looking in that aspect of what reacts faster, because the reaction center, if it is blocked by a steric group, that is a bulky group, then it undergoes the reaction slower. It does not mean it is not undergoing reaction, but it is undergoing the reaction at a slower rate. So this is the one we are actually looking at in this particular case. So the secondary bromide, even though the secondary bromide reacts slower as per normal conditions, here we have a smaller ethyl group and a methyl group. So we have two groups which are smaller, which is attached to the reacting center. So now the nucleophile has to come and attack from this side. Okay, so this is having a small group here, ethyl group. There is another small group here, methyl group. So the nucleophile can easily come and attack from this center. But let us look at the other case. In this one, what happens? Although this is a primary carbon, one side we have a very bulky tertiary butyl group. So this prevents the attack of the nucleophile. So due to this, what happens is this reacts at a slower rate. It is not that it is not undergoing reaction. It does undergo the reaction, but it undergoes the reaction at a slower rate. So that is what is the difference. So in this case, we can very well say the secondary bromide reacts faster compared to the primary bromide. So you cannot always say primary reacts faster than the secondary. You have to always look at the substrate very carefully to confirm which one will undergo the reaction faster. Because for SN2 reaction, the most crucial one is the steric hindrance. If there are bulky groups, rear side attack is very difficult. And if you simply go back to the reaction mechanism, tertiary carbon itself is too bulky, so it does not even undergo reaction by SN2 mechanism. So this is the one you have to always remember. You cannot simply say which one will react faster or slower without looking at the structure of the substrate. So always pay attention to the structure of the substrate and decide which one will undergo faster. So let me reiterate the same thing. We have to look for substituent size. So this is the most crucial one for SN2 reaction. because SN2 reaction is a rear side attack. So a bulky tertiary butyl substituents prevents the rear side attack. So the reaction proceeds slower. Okay. So this is how we have to identify which one reacts faster and which one reacts slower. So now let us look at what products are formed in these two particular reactions. So we have one substrate here, we have another substrate here. So this is treated with the sodium bromide in the presence of an acid at 50 degrees centigrade, and this substrate is treated with a sodium acid, and here there is a stereogenic center. Here also we have a stereogenic center. So we need to pay attention to what is the stereogenic center and what type of reaction it will undergo. Based on that, we will have to predict the product. How do we know which one will undergo what type of reaction? Some hints I am giving you right now. You may have to, we will of course see the answers, but before that, what you need to do is get few hints what type of reactions can be possible. Now, one of the clue here is we have a acid group. Okay, here we don't have a acid group, so that is the only thing which is different. Now, does it make any difference or not? We really don't know right now. Okay, we have to figure it out whether that presence of an acid makes any difference in this particular reaction or not. Now, there is a hint given here which says that leaving group ability. So that means, what is the leaving group ability? Here in this case we have hydroxyl, which is a leaving group. Here we have a bromide. So between hydroxyl and bromide, you already know bromide is a better leaving group than the hydroxyl. Of course, both will undergo substitution. Let us find out how the hydroxyl can be a leaving group in this particular case. So here we are continuing from the leaving group ability to leave. So we have here a OH group which is a very poor leaving group. That means this OH cannot leave that easily. But in this second case we have a bromide which is a very good leaving group. So that means this can undergo SN2 type reactions very easily. So this one may or may not undergo SN2 type reaction that easily. So we will see how it can be done. Now, there is one particular important information given here, which is a acidic condition. So under acidic conditions, what can happen? The protonation of this particular hydroxyl is possible. That is what it is written here. OH plus H plus gives H2O plus. Compared to OH minus, which is a poor leaving group, the H2O plus is a very good leaving group. So this is one of the hint you have to remember. Okay. So OH as such cannot undergo or cannot be replaced that easily. But when the OH is converted in the presence of an acidic conditions to H2O plus, that becomes a very good leaving group. Remember this. So let us look at the individual steps in this particular transformation. So the entire mechanism is written here. Now you can actually go through step by step. So in the first step, the lone pair of electrons on the hydroxyl oxygen is bonded to the H plus, that is the proton. So this is getting converted into a H2O plus. Okay, the H2O plus is a very good leaving group, so this is lost. So here we have minus H2O. Okay, water molecule is lost in this particular step, so that leads to a carbocation. A carbocation is generated on this particular carbon. Now this can be attacked by the bromide minus ion, so we end up with this particular product. This being, even though we have a hydroxyl which is pointing upwards, in the final product we have a bromide. We don't know what is the stereochemistry of this particular one, because we have a carbocation, and due to the formation of this carbocation, the bromide can attack from either side, leading to a racemic product, or both 50-50 ratio of the final product can be formed. So the stereochemistry cannot be identified in this particular product. That means it leads to racemization. So the product is racemized product is the one we are actually getting. And another important thing, the poor OH group, which is not a good leaving group, can be converted to a H2O plus, that is a better leaving group, by the reaction with or reaction carried out under acidic conditions. So let us look at the next sodium acid reaction with this particular bromide. We know bromide is a good leaving group, and let us see how the reaction proceeds here. So the sodium acid gets converted into Na plus and N3 minus. So this is the first step. In this first step, the acid is the nucleophile for this particular reaction. So we saw this sodium acid is split into Na plus and N3 minus. So in the next step, what happens is, this N3 goes and attacks this particular carbon from the rear side. That leads to the concomitant removal of the bromide anion. So we end up with a inverted stereochemistry at this particular carbon, because this is a SN2 mechanism, and this reaction is basically inversion of configuration takes place. So that means the bromide is replaced by the acid with inverted configuration. So in this particular case, we have the inversion of configuration, because this is SN2 reaction. So the inversion of configuration occurs at this particular carbon. So we had, in summary, we have studied about the various problems and how to solve the problems with respect to SN1 and SN2 mechanism. And we also have studied about the clues, like if an acid is given, so what hint it is giving. So all those things we have seen in this particular reaction, in this particular session. Thank you.